So, last time I said to you, and I understand that even I do not need to write anything about this, that every semi-simple Lie algebra is a direct sum of simple Lie algebras, simple non-commutative Lie algebras, because one-dimensional Lie algebra is simple but not semi-simple. I want to say that this actually we have. Simply last time I didn't want to pronounce it in such a way that people do not listen to me. If a Lie algebra, semi-simple, is not simple, then it has an ideal. This is the reason why it's not simple. If it has an ideal, then the orthogonal complement of this ideal is also an ideal. Ideals of semi-simple Lie algebras are semi-simple. And also I proved last time that if H is an ideal in a semi-simple Lie algebra G, then G is a Lie algebra, direct sum of H and H orthogonal. So it's the direct sum of two ideals. And then you proceed. If these ideals are simple, then you stop. If they are not simple, you apply to them the same procedure. So it is sort of very obvious. You split and split and split until you have the sum of simple Lie algebras, which are also semi-simple, non-commutative. But also I said that this decomposition is unique. Unique in a very strong sense. If you have a semi-simple Lie algebra, well, G, what else? And G okay, well, L is the sum of simple Lie algebras of all these H's and K's are simple. Then I want to say that actually this L is equal to M, and this the only difference between this decomposition may be that something is switched. So every K is one of H's, and every H is one of K's. Why? Take K1. Now I want to take intersections of this K1 with every H here. This intersection is an intersection in this universe, maybe empty or non-empty. Well, empty is 0 or non-zero. If it is 0, it's okay. But is it really possible that it is 0 for all I? Let me say no. Because this means that K1 also, I proved this last time, has zero commutativity with HA. If K1 has zero commutativity with all H's, then actually it has zero commutativity with G. So this is central. And semi-simple algebras, excuse me, do not have centers. Right? Center is, well, solved ideal. Well, so this is impossible. So not every, K1 has a non-zero intersection with one of H's. Now, if K1 and HI is, then what? This is an ideal in both K1 and HI. And it's not simple. It is not zero. So this should be both K1 and HI. This is all. So every K, K2 are the same. Every K is one of H's, every H is one of K's. Definitely only one of them. Even if, say, two H's are the same, then still we can establish a correspondence between K's and H's. If you do prefer, we can factorize the whole algebra. After we do this, we can factorize this algebra over K1 and do the same for the remaining part. So this is sort of simple proof. I want to add to this. It is equally easy, but maybe you prefer that I do not give details. Well, the details are here, because they both are exercises, and you will be happy to write solutions. I want to say that all ideals in this sum, all ideals in G are subsums of this sum. So just take several sums, take their sum, and it will be an ideal and no other ideals. The same proof, actually. Also, from this we deduce that two ideals which have zero intersection, intersection is zero, not only they have zero commutator, but also they are orthogonal to each other, follows from the same. So all ideals which are disjoint in the sense that the intersection is zero actually commute with each other and have and orthogonal to each other. Orthogonal to each other. All these H's are all orthogonal to each other by my construction. Questions? No questions, no answers. Next thing, very small remark. Probably you will even not happy that I mentioned it, but it's very simple. The killing form of Lie algebra is invariant. It was its first property. You remember what it means, right? I will use it, so if you don't remember, I will anyhow remind you. Other invariant forms. Well, certainly you can multiply your killing form by 2, 3, or any other number. It was also invariant. But essentially other forms. The following, yes, you are right. The following thing is sort of obvious. If the Lie algebra is simple, then if the Lie algebra is simple, then any two invariant bilinear symmetric forms are proportional. And this is sort of, again, obvious for simple Lie algebras. So if G is simple, say A and B, two invariant forms. I say invariant forms, meaning all the symmetric bilinear forms, real or complex dependently on the ground field with G. You certainly can present A and B as symmetric matrices using some basis in G. And if you consider let me assume that B is not zero. If both are zero, then I have nothing to prove. So let B be not zero. I consider this, A minus lambda B. This is a polynomial in lambda. Moreover, if the field it has roots. Moreover, if your field is R, then this polynomial has real roots. It's known to many people that in the symmetric case, this all the roots are real. You, by the way, can consider it just as a cohesive polynomial of A, because you can multiply by B inverse if B is not zero. No, you cannot multiply, but still, this is true. The same proof. Yes. Now we consider this equation and take a root lambda 0. Again, lambda 0 is a complex number, but if the field is real, this is a real number. Then I consider the form A. I can denote it, just to use the alphabet, by SC. So the form C, also an invariant form, right? But unlike, I don't know what, this form is degenerate, right? So this is degenerate, because the term is zero. So it has a kernel. It is a 1 second proof. I will not repeat it. It is, this line is in my notes. This is an ideal. Kernel of this form follows from the invariance. It's an ideal. And if G is simple, and this is not zero. Because, so if this ideal if it is simple. Since G is simple, then this kernel should be G. So kernel C is G. C is 0, precisely what A is lambda B. Okay? Now you can ask, why on the earth, why do I need to consider other forms? Are there other forms? Yes, there are. There are Killing forms which are defined by representations. So now we see that actually for every representation of a simple Lie algebra, its Killing form is just the Killing form of the algebra multiplied by some number. This number is 0 non-zero, but it is 0 only if the representation is trivial. Again, it is immediately clear. All this is written in more details in my notes, but I think you understand. I hope that well. What about the semi-simple case? It is not precisely the same, because in this case we have a sum of simple Lie algebras. Each has its Killing form. The Killing form of the whole algebra is the direct sum of these Killing forms, but we can multiply these sums by different lambdas. And we have some amount of invariant forms, which is not proportional. And this is actually, in the real life, it is very common, because representations, there are very much important representations of semi-simple Lie algebras. And it's very possible that a semi-simple Lie algebra has a representation whose Killing form is not precisely proportional to the Killing form of the algebra. It's multiplied by something on one component, by something else on the other component. It's common. What about 0 and non-zero? From what I said, it is clear that any invariant, if Killing form of a representation can be considered on every component of every simple algebra from the direct sum decomposition. And it is 0 only on those components on which the representation is 0. So I can say that for a semi-simple Lie algebra, for a semi-simple G, actually the Killing form B rho for our representation is non-degenerate on the orthogonal complement with respect to the Killing form of the algebra itself, to the kernel. Kernel is an ideal in the algebra on which the operation is 0. Certainly the form is 0 there. So this is what can be said. This might be important to us. I don't think I can say anything else about the uniqueness of invariant forms, at least now. Well, questions about this? No? Jared? Interested? Bob? No questions? As you prefer. Next thing, here I need to, I don't know how to call it, apology, because I'm going to speak about a very important thing. But for me, it will be almost nothing. I will use it just once for a proposition which also maybe will not seem too important to you. Probably I could somehow skip all this, but I'm glad that I have this opportunity, maybe not very honest, to introduce here and to discuss the so-called Casimir operator. For those of you who are crazy with algebra, I hope this is the empty set, but just in case. Just in case. You know, in algebra, when we consider algebras, there is such a thing, we probably will have to consider it, as the universal enveloping algebra. As it is an associative algebra, and as any algebra in the universe, it may have center. It is actually a very important problem. What is the center of the universal Wellbeing algebra? I'm not going to resolve this problem fully, but sometimes the center is quite big. But what I want to say is I am going to introduce one element without introducing the universal Wellbeing algebra. Actually, I want to introduce one element of this center. So let me do this, and then we will discuss some technical details. Suppose that I have a semi-simple Lie algebra. I think it is pointless to consider this construction for Lie algebra which are not semi-simple. But certainly some definitions, some first definitions will not require this. I prefer to no, from the very beginning, my construction from the very beginning will require it, yes. So we have a semi-simple Lie algebra, real complex, G. It is very much finite dimensional. Then Colin will ask me about Kac-Moody algebras, I will answer. But first it's finite dimensional. Consider a basis in it, G1, Gm, a basis. Then G possesses this non-degenerate, this is semi-simple, non-degenerate form B, which certainly gives rise in the usual way to a construction of dual, everything in particular dual basis. So dual basis, G1, Gm, I write dual. In this course I will not follow the tradition and will not be too accurate with lower and upper indices, but here I prefer to have this notation. So they are dual in the sense that the form B applied to this is delta Ij. You understand? So this is a definition of a dual basis. By the way, I want to say immediately, what if you have some element G in G? You want to present it as a linear combination of this or this, of this or this basis. I can write this G is equal to B G I G times G I, the sum over G, or this is a very common trick in linear algebra. You know it maybe not in this notation. You certainly know how to, if you have a vector in space, how to find its coordinates with respect to some, well, orthonormal basis. So basis there should be said that the dual basis is the same. But this is also true. And if you don't believe, take any gk and take inner products of b of g with gk and this with gk. We'll see that this is the same. So it's k should be one case upper and one case lower. It is very simple. Well, it is just a remark. Then the definition. This is the following. Suppose that we have some representation rho. I define an operator C of rho. And the definition is C of rho is the sum over I rho of gi rho of gi. This is the definition. Before you ask very natural questions, I want to say one more thing. The main reason of existence of this Casimir operator, Casimir starts with C. is that it is actually a marginal homomorphism. That actually for any G in G, C rho of G is equal to rho of G 0. This is all I need to know about this operator, but certainly you could have two questions. I will try to answer questions. Question number 1. Maybe not very important, but still, does it depend on the basis? My first word was that I chose a basis in G, and then it was used in this construction. What if I choose a different basis? Will be the same. The answer is yes, and I will give you explanations if you really need them. The second, not question, but natural request is to prove this. Both are immediately clear. Actually, the first question, I answer it. I mean, the independence of the basis. But certainly it is, again, not for algebraics. Because true algebraics should say that it is obvious and no other questions should be asked. Why? Because how to prove that something which is defined by means of a basis or by means maybe of a Riemannian structure on some manifold or maybe by means of something else actually does not depend on this. You simply need to find an equivalent definition which doesn't use any arbitrary choices. And certainly it can be done with this scaling form. Maybe I even shouldn't say anything else. So an alternative definition of a killing form. Excuse me, killing operator. What is a killing form? What is a bilinear form? A bilinear form on val on G is an element on G of the dual space to the tensor product of G in itself. Or if you wish, I hope you understand this notation from linear algebra. If not, you can ask. Yes. Now, the non-degenerate form B gives rise to an isomorphism B between G and G prime, right? Well known that for finite dimensional spaces, this there is isomorphic because they have the same dimension, but the bilinear form is precisely what you need to establish this isomorphism. So this is isomorphic, canonically isomorphic to G tensor G. Now if you do all the computations, you will see that if you take B here, then it corresponds to the to an element of this, which is this. And it, hence it doesn't depend on the basis. For any basis it corresponds to this. You can speak instead of the operators here, you can Casimir operator, you can speak of Casimir element in this G tensor G. Although in reality it is an element rather of the universal Arabic algebra. So in this way you see that actually this element of G tensor G doesn't depend on the basis. It is defined simply by B. We have B, the killing form. And it is defined in a direct way like this. Actually, there are other possibilities which probably will be preferable from the point of view of students in linear algebra, or maybe of people who closer to physics and prefer to have bases in their spaces, as physicists usually do. If you make a basis change, so you replace the basis gi by some basis g prime I, then g prime I and gi are related by the transition matrix. Then the dual bases are also related by some matrix. And this matrix actually is the transposed inverse. These two matrices are related to each other. After which you consider the sum gi prime tensor g upper I prime, plug the expressions through gi and gi prime, with obvious transformations of matrices, you see that they are the same. So it's very easy to prove, and this is done actually in my notes. I shamefully did this proof, although I understand that this is this reveals my maybe not too easy relationship with algebra. Although I am an algebraist, but still relationships are not. Yes. As to the second part of the story, let me erase this. It is still easier. So what do I need to prove? I need to prove that for any g in G, two things are the same. Rho of gi, no, rho of gi, rho of g, and this. They're the same, right? I prefer to do it using simple notations, the same thing. But I prefer to, instead of considering these operators, I prefer to consider elements of tensor products. So I have two things. This rho, that's gi, G, and this. Well, maybe it's better if it's just this. So look at this, these things. What happens when we move this thing through this and through this? You can move it, but at every step, there are two steps. You will get a commutator. So the difference of these two, actually, is the following. The difference of these two. The sum rho of gi, rho of g I commutator gi and g, and the sum rho commutator of gi and g, rho of gi, right? It is all written in my notes, but let me say briefly. Actually, this thing is is here. This thing, the sum over k, I hold it here, b of gi g, let me write k, gk, I will write it like there, gi, g, right? Rho of gk. The sum now will be for k and I, right? Okay? No. Row. One more. Yes. Actually, and here row OG. So this thing is equal to this times GK, row OGK. Yeah, I see now what happened. Row OGK. And here so I consider this now, right? It will have row OGI. Now it's okay. And in the same way you transform the other sum. You will have actually the sum of the same things. The sum of the same things. With only difference that you will have different coefficients. The sum of the same things with different coefficients. And if you compare the coefficients, you see immediately that they're equal to each other because of the invariance of the form B. This precisely the invariance. So this is how it is done. I don't want to waste the whole word on this. You take this, in both cases, you replace the commutator by an expression like this. You understand? After which, both sums, which should be, the sum of them should be equal to 0. They're not equal, the sum of them should be equal to 0. And both of them are sums indexed by two numbers of the same expression, only with different coefficients. And the coefficients, the sum of the coefficients for every k and I are zeros because of the invariance of the form, and this is the invariance of the form. So this is done like this. Again, details are in my notes. One very small remark. In this form, I used orthogonality with respect to the form B. But I said to you many times that there are other forms. In particular, you have a representation. Then you have the killing form related to this representation, right? And it is not non-degenerate anymore. So let me write it. I want to denote a new operator. Just not to confuse with C of rho, I will write C super rho. Rho is a representation now. And there is the form B rho, which is not degenerate on kernel rho orthogonal. I said this to you. So actually we can take dual basis, not in G now, because in G they know it will dual basis for a form of degenerate, but in this space. So you take G1 GM, G1 GM dual basis in this space. If rho is faithful kernel, then again in G. But if replacing rho may be 0 somewhere, has a kernel, then you have this. And all the rest is the same. The definition which you can make, which you can design using the two dual bases, give you an operator C rho which doesn't depend on the basis, and operator V, again, V is a space representation, and commutes with the representation. By the way, I didn't say to you, but probably this is the most important property of the Casimir operators, even if you return back, but for this also. Just imagine that an operator, Casimir no, compatible with the operator, commutes with the operators of the representation. Imagine that your representation is irreducible. What do you think about this operator? Scalar. Scalar. Why? Well, if you have this operator, then probably it has an eigenvector. I consider the complex case. In the real case, the same will be done by complexification. So a complex case has an eigenvector. You apply all elements of your Lie algebra to this eigenvector. You get some vectors. Apply again to them elements of the algebra. Do it as many. So you have some set of vectors in your space V, which are obtained from one vector by various operators of the representation, maybe repeated several times. You understand? And since the Casimir operator commutes with the representation operator, all these vectors will be eigenvectors with the same eigenvalue. And they span a subspace, but the subspace is a subrepresentation, obviously from construction. And if your representation is irreducible, this is the whole space. It contains your initial vector and is a subrepresentation. So, and in this case, in this set, in this way, we see that the Casimir operator, if the representation is reducible, then the Casimir operator is a scalar operator, just number. This is actually the main property of Casimir operators, and it is, I'm very sad to say that we probably will never use it. But this is why this exists. That such operators actually distinguish representations. And if the representation is reducible, it helps to sometimes to obtain irreducible components. Now one more thing about this. The operator B rho, if rho is not zero, then this operator, let me say this, is not nilpotent. You can think what of that? You will see what of that. In both definitions, in my initial definition of the Casimir operator or in this new definition, let's answer a very simple question. What is the trace of C? Rho or trace of C rho? But you see, what is this? What is this? Let me consider this. It is the operator is the sum Gi, rho Gi, rho Gi, right? Very interesting. Well, trace of this. What do you think the trace of this? I personally think the trace is 1. Because this is B, trace of this is B of GB rho of GI, which should be 1 simply by definition of the dual basis, right? So this is the sum of ones. And the number of the ones, so this is just the dimension of the space, number of basic elements, by basis elements. And this is all. Because if the representation is not 0, then this is not 0. And if an operator has non-zero trace, it cannot be nilpotent. Now I said to you that the whole goal of considering Casimir operators, unfortunately, is proving of a very, how to say, small and not looking important proposition. Although it is sort of interesting. So an application of Casimir operator to the representation theory. Suppose we have a representation of a semi-simple Lie algebra. Then I do the following. I get two spaces, V super row and V sub row. The super row is a space of invariance, which means that those elements of V for which row G, well, let me see, of V is 0 for any Xi in G. Special invariance. This is the following thing. I consider span of all I take all vectors V and apply to them the operators of the representation. Some subset of V, and I span a subspace by it. It is called V row. By the way, there exists a word which some people love, coinvariance. Well, actually, dualization is very actually fruitful idea in algebra, in any kind of algebra, and here also. Coinvariance, by definition, are elements of the quotient of V over V sub row. You understand? For those of you who love homology, one of this is cohomology, invariance is cohomology, and coinvariance is homology, but I will not say much about it. What I want to state now is something which shows that, at least in the finite dimensional case, no difference between invariance and coinvariance. Look. Proposition. With all these arbitrary semi-simple Lie algebra and all arbitrary representation. Well, first thing, it is obvious, should be also said, that both V row, V upper row, V lower row are sub-representations. Both are preserved by the action of, it is obvious. Invariant space, you know, any element of the algebra actually sends this to 0, so it is invariant very much. And excuse me, this is not precisely wrong, but looks unusual. Row here and row here. The statement is that invariance form a sub-representation. This space V row is also a sub-representation, but what is more important, that we have direct sum decomposition. Direct sum decomposition. And this statement, which seems very much elementary, I do not know a proof of this which does not use the Casimir operator. I have just several minutes, so let me say something, but certainly I will repeat this next time. Certainly this statement, as all many other statements like this, are proved by induction. Induction with respect to the dimension of V. If the dimension of V is 0, then nothing to prove. Actually, if it is 1, also nothing to prove. It is very easy to understand. But 0 for 0 is nothing to prove. So I suppose that this statement has been already proved for all representations, for which of dimension less than dimension of V. Okay? So how to make the induction step? If we are able to split V into two parts, non-zero parts, so if V is sum of two representations, then certainly everything will work. because for each of those representations I have the decomposition, and certainly the summation will give it for V. Is a representation V a sum of other representations? You can say it is not important for the proof, that V may be reducible. Actually, if V is irreducible, then also we have basically nothing to prove, because the invariance will be 0 and the co-invariance V rho will be the whole V. I do not need this, but it is so. Still, how to split V into two parts? You know, there exists effect from linear algebra. Again, I refer to those of you who may teach linear algebra. Suppose that we have an arbitrary linear map of some vector space into itself. Then let me consider two things. First, the intersection of all kernels, no, the union of all kernels of the powers. So actually I consider all elements which are annihilated by some power of f. This will be W1. Now W2 will be the intersection of all images. So this consists of those vectors in W which actually belong, which belong to the images of f, of squared, of cube. You understand? And the fact from linear algebra follows immediately. I do not have time to say more about it. Follows immediately from the general form that W1 and W2 form decomposition of this. After this, my last word today. After this, I apply this fact not to just f, but to the Casimir operator of this V. And you get the splitting of V in the sum of two sub-representations. Actually, one of them may be trivial, but if f is the Casimir operator, we can say a lot about these spaces. And this is enough to prove my proposition in just several lines. I will do this next time. I hope to do more today, but it is all.